Mic check. Mic check. What's up, dog? Why you face palming? Ah, why you face palming? Huh? Huh? I got what? I probably just showed my stream key, didn't I? Did I? I feel like I did. Feel like I did. I don't think I did. Mm-mm-mm. What are you doing? Yes, I'm talking to you. Look comfortable. You look comfortable. I don't know.
So I have a curve here that represents y is equal to f of x. And there's a classic problem that mathematicians have long thought about. How do we find the area under this curve, maybe under the curve and above the x-axis? And let's say between two boundaries. Let's say between x is equal to a and x is equal to b. So let me draw these boundaries right over here. That's our left boundary. This is our right boundary. And we want to think about this area right over here. Well, without calculus, you can actually get better and better approximations for it. How would you do it? Well, you could divide this section into a bunch of delta x's that go from a to b. They could be equal sections or not, but let's just say for the sake of visualizations, I'm going to draw roughly equal sections here.
Oh,
so
that's my
the first,
microphone.
that's the second, this is the third, this is the fourth,
Oops.
this is the fifth, and we have the sixth right over here.
Here you go.
And so each of these, this is delta x, let's just call that delta x1, this is delta x2, this width right over here, this is delta x3, all the way to delta xn. I'll try to be general here. And so what we could do is, let's try to sum up the area of the rectangles defined here. And we could make the height, maybe we make the height based on the value of the function at the right bound. It doesn't have to be. It could be the value of the function someplace in this delta x. But that's one solution. We're going to go into a lot more depth into it in future videos. And so we do that. And so now we have an approximation.
Well, I ain't crying in the middle of Chanel. Wait. Don't do that. Okay.
The area of each of these rectangles are going to be f of x sub I.
Don't do that, Debbie. PT test for what? Oh, you guys got. Oh, yeah. I forgot. I'm sorry, damn.
The x sub I is the right boundary the way I've drawn it.
Here you go, here you go.
There's a classic problem that mathematicians have long thought about. How do we find the area under this curve? Under the curve above. And let's say between two boundaries. Let's say between x is equal to a and x is equal to b. So let me draw these boundaries right over here. That's our left boundary. This is our right boundary. And we want to think about this area right over here. Well, without calculus, you can actually get better and better approximations for it. How would you do it? Well, you could divide this section into a bunch of delta x's that go from a to b. They could be equal sections or not, but let's just say for the sake of visualizations, I'm going to draw roughly equal sections here. So that's the first, that's the second, this is the third, this is the fourth, this is the fifth, and then we have the sixth right over here. And so each of these, this is delta x, let's just call that delta x1, this is delta x2, this width right over here, this is delta x3, all the way to delta xn. I'll try to be general here. And so what we could do is, let's try to sum up the area of the rectangles defined here. And we could make the height, maybe we make the height based on the value of the function at the right bound. It doesn't have to be. It could be the value of the function someplace in this delta x. But that's one solution. We're going to go into a lot more depth into it in future videos. And so we do that. And so now we have an approximation where we can say, look, the area of each of these rectangles are going to be f of x sub I, or maybe x sub I is the right boundary the way I've drawn it, times delta xi. That's each of these rectangles. And then we can sum them up. And that would give us an approximation for the area. But as long as we use a finite number, we might say, well, we can always get better by making our delta x's smaller, and then by having more of these rectangles. Or get to a situation, here we're going from I is equal to 1 to I is equal to n. But what happens is delta x gets thinner and thinner and thinner, and we have an n gets larger and larger and larger. As delta x gets infinitesimally small, and then as n approaches infinity. And so you're probably sensing something. Then maybe we could think about the limit as, we could say, as n approaches infinity, or the limit as delta x becomes very, 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 very small. And this notion of getting better and better approximations as we take the limit as n approaches infinity, this is the core idea of integral calculus. And it's called integral calculus because the central operation we use, the summing up of an infinite number of infinitesimally thin things, is one way to visualize it, is the integral. That this is going to be the integral, in this case, from a to b. And we're going to learn a lot more depth. In this case, it is a definite integral of f of x dx. But you can already see the parallels here. You can view the integral sign as like a sigma notation, as a summation sign, but instead of taking the sum of a discrete number of things, you're taking the sum of an infinite number of infinitely thin things. Instead of delta x, you now have dx, infinitesimally small things. And this is a notion of an integral. So this right over here is an integral. Now, what makes it interesting to calculus, it is using this notion of a limit. But what makes it even more powerful is it's connected to the notion of a derivative, which is one of these beautiful things in mathematics. As we will see in the fundamental theorem of calculus, that integration, the notion of an integral, is tied closely to the notion of a derivative. In fact, the notion of an antiderivative. In differential calculus, we look at the problem of, hey, if I have some function, I can take its derivative, and I can get the derivative of the function. Integral calculus, we're going to be doing a lot of, well, what if we start with a derivative? Can we figure out, through integration, can we figure out its antiderivative, or the function whose derivative it is? As we will see, all of these are related. The idea of the area under of curve, the idea of a limit of summing an infinite number of infinitely thin things, and the notion of an antiderivative, they all come together in our journey in integral calculus. What we're going to do in this video is introduce ourselves to the notion of a definite integral. And with indefinite integrals and derivatives, this is really one of the pillars of calculus. And as we'll see, they are all related, and we'll see that more and more in future videos. And we'll also get a better appreciation for even where the notation of a definite integral comes from. So let me draw some functions here. And we're actually going to start thinking about areas under curves. So let me draw coordinate axes here. So that's my y-axis. This is my x-axis. Actually, I'm going to do two cases. So this is my y-axis. This is my x-axis. And let's say I have some function here. So this is f of x right over there. And let's say that this is x equals a. And let me draw a line going straight up like that. And let's say that this is x equals b. Just like that. And what we want to do is concern ourselves with the area under the graph of y is equal to f of x, and above the x-axis, and between these two bounds, between x equals a and x equals b. So this area right over here. And you can already get an appreciation. We're not used to finding areas where one of the boundaries, or as we'll see in the future, many of the boundaries could actually be curves. But that's one of the powers of the definite integral and one of the powers of integral calculus. And so the notation for this area right over here would be the definite integral. And so we're going to have our lower bound at x equals a, so we'll write it there. We'll have our upper bound at x equals b, right over there. We're taking the area under the curve of f of x, and then dx. Now in the future, we're going to, especially once we start looking at Riemann sums, we'll get a better understanding of where this notation comes from. This actually comes from Leibniz, one of the founders of calculus. This is known as the summa symbol. But for the sake of this video, you just need to know what this represents. This right over here, this represents the area under f of x between x equals a and x equals b. So this value and this expression should be the same.
¿Qué pasó? Go to sleep. You gotta work tomorrow. Are you making a stank face? Are you making a stank face? Huh? It's always something with you. You know how? How what? Oh no way! It's called the sun. The sun was hot today. Did you hear yourself? When is the sun cold? The sun was hot today. What word? Can you tell me? Can you just tell me? Oh, that make funny. Can you tell me? I'm not. I'm not. I'm serious. I'm serious. I won't say anything. Whatever. Whatever. Means what? Means what? Okay. Whatever you say, Deborah. I'm making fun of you. Okay. Okay. She made 19 $19,000 plus three. Oh, it's already added. So she made $19,000 from month one to month five. I wish I didn't live next to the pool. That's terrible. Maybe I should have what? They have a time. No one follows it. I need a peaceful year round. What's up, Matsu? What's going on, man? We're just chilling. How are you doing? Must be good at math. His name's the mathematician. Nah, man. I'm on the phone. That's why. I don't want her to make fun of me. Why are you looking at me like that? But thank you. 0.3. That makes sense. All right.
It took 20 minutes before Jughead noticed that his hot tub had sprung a leak. Once he realized it, he opened the hot tub's drain and the rest of the water rushed out in 40 minutes. The rate at which the water drained from the hot tub, in gallons per minute, is shown. How many gallons of water were in the hot tub before it started to leak? So let's see what they have over here. So they've plotted time, or they plotted gallons per minute versus time within minutes. And so we see here, this blue line, this is the rate at which water drained from the tub. Rate at which water drained from the hot tub. So at minute 0, the water wasn't really draining from the hot tub. And then more, not just more drained, but the rate at which the water was draining increased. So 10 minutes into his bath, it was the water was draining at a gallon per minute. And then 20 minutes into his bath, water was draining at 2 gallons per minute. And then he noticed it and he opens the drain. I guess he wants to accelerate the end of his bath. So he opens the drain and then all of a sudden water starts draining out at a much higher rate, at 20 gallons per minute. But then that decreases. And so we could think about physically why that might decrease. Maybe there was just it was just less pressure or whatever.
I'm going to UTA in Arlington in fall.
We're not going to go into the physics of it, but we're just
University of Texas at Arlington.
going to take this chart as fact. But the rate at which the water drains decreases all the way to the 60th minute, which is 40 minutes after he opened the drain. 60th minute, all of the water was drained. All of the water was actually drained out. So given that, how do we think about how many gallons of water were in the hot tub?
Am I from Florida? No. Never been to Florida. Closest I've been is Georgia. I used to live in Georgia. That's it.
Before it started to leak. And I encourage you to pause the video and try to see if you can figure it out yourself before I work through it. Well, to answer
That's because I was flying. There's plane content on my channel. Is that why? We're flying planes in Texas too. Even though
this question, how many gallons of water were in the hot tub before it started to leak? That's answering the same question as how much total hot water drained out. So how much drained out. And to think about that, we can just kind of go back to what we knew before we learned about calculus. If I have something happening at a fixed rate, so let's say this is gallons per minute.
or you're in AP calculus in 10th grade in high school. Well, I already took college calculus, like calculus 1 and 2, but this was 2 years ago, so I forgot, kinda. And I switched my majors from computer science to aerospace engineering, so I'm just trying to get a refresher essentially. But I always
So this
appreciate
is still
help
the
though.
same,
Yeah.
the same context. I guess you could say this is time in minutes. And let's say things are draining out at a constant rate. If you wanted to figure out how much drains out over a certain interval of time, let's say this interval of time right over here, let's call that delta t over delta t. You would just multiply the rate over that interval of time, which would be which we could represent by this orange height right.
Am I gonna work for NASA? If they give me a job, sure, I'll take it. It's not easy though. That's the goal. Boeing, NASA, Lockheed, any of those. Those are perfect.
Right over here times the amount of time that passed by, which essentially would give you the area under the curve over
It's a
that
lot of
interval.
hard work.
The area under the curve over that interval. This area would tell you the gallons that drained over that delta T. And this doesn't just apply when you have a constant. When you have a constant rate, if your rate looks something like
SAT score. I took the SAT like 2019. This was what? How many years ago was that? Jesus. 6? I don't even remember, honestly. I'd have to go to college board and like pull it up and stuff. Yeah, that was 6 years ago. I graduated high school in 2020. So that was a long time ago. It probably wasn't that good though. Can I pull it up?
that has drained.
Did you get in college for free? You paid some extra money. I paid extra money for college. I didn't get in for free. Well, my scholarship wasn't like completely academic, so I paid out of pocket, but I got a scholarship for something else that's not related to academics whatsoever. So I only had to pay like, I want to say, 2 grand a month initially when I was going to Sam Houston. 2 grand a month, 2 grand a semester, not a month. Jesus. In high school, did I take any AP classes? Nope. Like I said, I had no idea what I was doing in high school. Zero AP classes. I finished. I had to take most of those classes in college. I went to community college for 1 year. Then I went transferred to actual college. So I mean, the fact you're taking AP classes though, that means you're obviously ahead of the game right there. There you go. So
You the gallons that drained over that delta T. And this doesn't just apply when you have a constant. When you have a constant rate. If your rate looks something like this, as we've seen in other videos, you could figure out the amount that has drained.
you're in Florida. Where are you trying to go? What college?
The amount that has drained in a specific interval, let's say this interval right over here, by essentially figuring out the area under the curve over that interval. And the units work out. If you multiply gallons per minute times minute, this area is going to be in terms of gallons. This area is going to be in terms of gallons. Another way you could think about it, and this goes back to, well, how do you figure out the area of a trapezoid right over here? Well, the area of a trapezoid, you could find the average height of the trapezoid, which would be the average of the beginning and the end period. You take that average over there, and this would work for a line like this. If you take that average height and multiply by the change in time, you are going to figure out that area. And that's another way of thinking about it is you're taking the average rate over that interval times the interval, and that's going to give you the total number of gallons. And so we just have to apply that idea over here. We just literally figure out the area under the curve over the entire interval when the water was actually leaking or draining. So essentially the area under the curve between 0 minutes and 60 minutes. And so it's going to be this area. Let's put that in magenta. Plus all of this area under this part as well. And to help us think about that, I'm just going to split that up into some sections. So this triangular section up here. So I have this triangular section. I can just think about this as a trapezoid, but I'm just going to split it up into a triangle and a rectangle. And then I have this section right over here in green. So what is the area of this entire thing? Well, the area right over here, we have 20 gallons per minute. So 20 minutes. 20 minutes times 2 gallons per minute.
Yeah, but do you know where you're trying to go? You want to go for free or from Florida? What's your dream school? There you go. It's your dream school. If you get into one in Florida, University of Florida, UCF, you know, UF, yeah. Figured. I figured. UGA was nice when I was in Georgia. There's a 0% chance I was gonna get in there though. I believe, man. We'll get that SAT, ace it. Now that I think back, I didn't even like study the night before, nothing. Like the weeks leading up to taking the SAT, I did not study. I just showed up for my calculator. I still remember we took it in this class, and there was probably like, I want to say 15 people in there. Yeah. Even like when they give us the PSATs in high school, like the school would administer those. I didn't take those serious either. So yeah.
Gallons per minute times 1/2 times 1/2 gives us the area under this triangle. So that is going to be 20 gallons. We see that the units work out nicely. And so that's essentially how much is drained out in the first 20 minutes.
You fall asleep during the exam? That's almost impossible, man. What do you mean? You're terrible. I'm terrible for falling asleep. I don't get sleep before the exam. Oh, the night before? Yeah. Just you said when did you say you're taking it? In a month, I think you said. Hold on. You're taking it in 2 months. Start studying right now. Just pull up the YouTube videos. That's it. Pull up the YouTube videos, SAT preps, all that. Yeah. Start doing those. Because if you try to 2 weeks, a week before, that's when you try to start studying like I did, you're not gonna do very well. A lot of questions, now that I think back to it, they're like, it's nothing crazy. If you're taking AP calculus in high school, I don't remember seeing any calculus questions on my SAT whatsoever. I mean, not it's like all the questions aren't. There's nothing outrageous. It's just I was stupid at the time, essentially. So start studying now. That's like the biggest thing. Don't wait. YouTube videos, even if it's once a day. You're good at math but poor at English. Yeah. Uh, well, the English section isn't like it's not English. That's the thing. Like the way they teach English in high school, I guess it's not really English. Well, maybe it's because I speak English naturally. But it's more about like it's like it's different from like learning German in high school or Spanish. It's completely different. You're actually learning the language. In English classes, you're not actually learning English. I'm trying to think of what they even cover on there, the reading section. Oh yeah, the writing essay. Yeah, yeah. So you got to write an essay, I believe. I don't. Yeah, I wasn't a fan of that either, honestly. I think you have to write an essay. I don't remember how it went. Yeah, I think there's a reading section and there's a writing section. No, I could be wrong. But yeah, it seems like you're good at math, so that's fine. But tips for English, uh, yeah, there's probably people who cover it on YouTube. You got 460 in English, 600 in math. What's that a total of? Okay, I can, but I don't want to. Leave me alone, Deborah. 6 plus 4 is 10. Yes, thank you. 1060. Yeah, yeah on the PSAT. Yeah, yeah. I'll just say hop on YouTube SAT reading sections. There's gonna be people all the way. Yeah, like the fill in the blank. Yeah, predict your SAT. So me on the, I'll tell you this, on the PSATs, I did worse than I did on the SATs. So if my SATs were usually a little better, it wasn't like astronomically better, just a little. I want to say by maybe, I probably like on the PSAT, I probably got like 1,000. I'm gonna be honest with you. But I ended up getting probably, I want to say, if I remember correctly, probably low 1200s on the SAT. So if you got 1060 on the PSAT, you're gonna do a little better on the SAT. But like I said, UF, I don't know how competitive it is, but UGA, like these people were getting 1600, 1590s. You know, had 4.4. I didn't even like when I was in high school. I didn't even know you could break 4.0 GPAs. Motherfuckers was getting 4.5, 4.5s. I'm like, okay, so I'm not gonna make that, obviously. You know, so yeah, if you want to go to college for free, you gotta do, start studying. That's for sure. And then depending on your financial situation, obviously you can make it work. With I don't know what grants and stuff Florida has. Pull up my high school grades. Let me see if I can find a transcript. I might actually have one on my phone. I actually might have this. Hold on. My high school grades are terrible. Well, uh, damn. Let me see. Do I watch Castaneda's feed? No. Not really. I'm not on Twitch like that, honestly. Wait, you're in 10th grade. You're a sophomore? Where you got time, man? You can take the SAT like what? I think 3 times? You're good. Or twice? Or as many times as possible? I don't even know. Yeah. Uh, you kidding me? I know I have this. No. Ah, I found it, but it's in a physical copy. So I don't know how I'm gonna show it on screen. Look at me, Deborah. This is for you right here, okay? I was a great student. Look, what does that say? Student of the month. Okay? For the whole English department. Okay? What is this? First semester phenomenal 5. Yep. What is this? Oh, I was a German student of the something. I don't even know what this says anymore. I can't speak German anymore. Student of the day for German or some shit. Right. Elite 8. Look at that. Phenomenal 5, Elite 8. Yep. That's my actual diploma. My teacher's notes. Oh, I miss high school. All right. Yeah, no, I had a 3.3 GPA. That was terrible. I had a 75 in physics. Oh my god. 3.3 in high school. That's terrible. Not school. I never used to do my homework. Like he couldn't pay me to do my homework. It was bad. I actually started trying college though. You know, look at that. Can you see that? What does that say? Okay. Dean's list. Everything. It was great. There's nothing to see. It just says Dean's list. That just means you got a 4.0. Yeah. And president's list and all that shit. I don't remember. I don't know. It's people playing music at the pool. I'm good. You'll be fine. You don't need it. You're good. I was trying to find this. Here it is, though. Here you go. Terrible. 78 in American Lit. Zero AP classes. Zero anything. That's 75 in physics. Then my last semester got canceled because of COVID. So yeah, I was a terrible high school student. 3.96. That's really good. What do you mean is that good? That's great. Well, I mean, for high school, if you want to, your goals are free college. My goals were just not. Like, I didn't even have goals. So, um, I guess 3.96 is pretty good. I don't know how that works anymore. Honestly, I don't remember. Because for like full rides, you definitely have to have a perfect GPA, super high SAT score. But then again, you don't have to get a full ride. If your parents aren't rich, I don't know if there's financial aid and stuff. You have a lot of grants and stuff. So if you get even a half of scholarship that pays for half, financial aid can cover the other half, and then there you go. You got free college. Yeah. So, but 3.96 is pretty good. It's really good for sure. Yep. This was the most fun right here. German. German one, two, three, four. Oh, I did take honors. Never mind. Honors German three. There you go. Honors German four. Those are my only honors classes. Honors. Oh wait, is that what the H means? Honors? No, maybe. I don't know. Honors forensic science, maybe. Yeah. I never took AP. Yeah. Has my old address on here. Don't worry, I don't live there anymore. I live in a whole nother state now, actually.
Minutes. And then this green area is going to be 40 minutes. 40 minutes times 10 gallons per minute times 10. And actually, maybe, the units, since I'm breaking it up in this strange way, I'll just multiply. I'll just figure out this area in a unitless way. So 40 times 10, which is equal to 400. And then finally in blue, I have 40 times this height right over here between 10 and 20 is another 10. But then I'm going to multiply that times 1 half. So it's going to be 40 times 10 times 1 half, which is going to be 200. And so you add all of these together, these areas together, you're going to get 400 plus 200 is 600 plus 20. You're going to have 620 gallons. 620 gallons is how much water in total drained out, or how much water was in the tub before it minutes, 20 minutes times 2 gallons per minute, 2 gallons per minute times 1 half. Times 1 half gives us the area under this triangle. So that is going to be 20 gallons. We see that the units work out nicely. And so that's essentially how much is drained out in the first 20 minutes. And then this green area is going to be 40 minutes times 10 gallons per minute times 10. And actually, maybe, the units, since I'm breaking it up in this strange way, I'll just multiply. I'll just figure out this area in a unitless way. So 40 times 10, which is equal to 400. And then finally in blue, I have 40 times this height right over here between 10 and 20 is another 10. But then I'm going to multiply that times 1 half. So it's going to be 40 times 10 times 1 half, which is going to be 200. And so you add all of these together, these areas together, you're going to get 400 plus 200 is 600 plus 20. You're going to have 620 gallons. 620 gallons is how much water in total drained out, or how much water was in the tub before it started to leak, or the hot tub there. This is quite big for a regular tub, but this could be like a jacuzzi or a hot tub.
You should be asleep. Oh, this was from middle school. Never mind. Mr. Wolfgang. Wolfgang. Flughafen. Oh, I got it right here. Got the paper copies. Look at me, I'm reminiscing. I actually ripped one, like I was mad. So I actually ripped one of these because I was mad. This was in 2023. I was tired of this fucking school. I was angry. I just ripped it, threw it away. Yeah, it's just a piece of paper. Doesn't mean shit. Drains over there, water out of the tank. The drains close to there. I'm not doing this. Uh, 375. Let me just take the area, right? So this is. Hmm? Sure. Kind of. Yes. Is the gallons lost per minute? Yeah. The rate at which water drains from the tank. Okay. Or did he? I'm confused. His
That was
go to
something.
the end? No? Fair enough. Alright, so this would be 60 times 2, which is 120. And then this would be 60 times, well, 8 divided by times 1/2. So 1/2 times 60 times 8. What's 8 times 6? 48. 48. So 480. Alright. Mm, I don't think you're stupid. Don't worry. Mm, 480 divided by 2. 48 divided by 2 is 24. 240. I double checked you in my head. That's why I agreed with you. Yes, I did. I didn't just take your word for it. It's 240 plus 120, 360. Would it be 360? Bruh, no way. Because it's draining at 10 gallons per minute there. So it doesn't even make sense if there's 360 left. Oh, so that just means 360 has drained out. So no. So it'll be 375 minus 360 will be the answer. Okay. That makes sense. 15. Maybe? Hey, let's go. Alright, that makes sense. I thought there was 360 left. I was like, that makes no sense. But no, 360 is drained out. Freight train leaves station on 4.5 hour trip. The graph below shows the train's velocity as a function of time. How far does the train travel? I don't know. Alright, so we got X right here. It's 0.5. So 1 over 2 times 40 times 1 over 2. So 1 over 4 times 40. So 40 over 4, which is just 10. It's 10. And then this is 0.5 to 3.5. Oh, it's a difference of what? 3? Right? 3.5 minus 0.5 is 3. So this is just 3 times 40. Okay. And the other side is 1 over 2 times 3.5 to 4.5. That's 1. So 1 over 2 times 1 times 40. So 40 over 2, which is 20. So this is 140, 150. The graph below shows the train's velocity as a function of time. Hmm? Yeah? Yeah? Why do you want to come in here? Why do you want to come in here? I don't want to spend time with you. Hmm? Hold on. They say the sun. What's up, Queen? I I forgot where I was. Damn. 150. How far does it travel? I think it's 150. Or 150 is the velocity. Or it's just the miles, rather. Yeah. Maybe? Hey, this is easy. This is just basic. I'm not doing this. I'm being this right now. Yeah, what? Mm. Mm-mm. But it'd been in Kenya and you'd have been making $10 a day. But it would have been in Kenya and you'd have been making $10 a day. Uh-huh. Hmm. Hmm. Quit reminiscing. Get to work. No matter. Comparison is the killer of all weight. Okay then. Quit comparing. You are on your own journey, man. Takes a little longer sometimes. Mm-mm. 5 and 10. 50 times 5. I don't want to do all this. I just want to get to the basic integrals part. I need a refresher, not a full course. A bunch of rectangles and triangles. Yep. I think it's free for everyone. I'm pretty sure Khan Academy is free because it's a non-profit. So they allow you to donate, but you don't have to pay for a membership. So yeah, this is what I need: the application of integrals, not the. What's a Riemann sum? I don't remember. Do I live with my family? Yeah. Family, singular, not the whole family. Yep, yep, yep. Let me watch a couple of Coursera videos and I'm gonna call it a night. Good night, Deborah. You're asking too many questions, Mr. Mathematician. Do I have a girl? Hmm. You're asking too many questions. What if I know you in real life and you're just in here, you know, sneaking?
So they basically have this ability. Today, let's talk.
You don't really know me. What do you mean, really?
About orbits. One of the main things about orbits is the altitude that the satellite or the spacecraft is at. So there are three main areas where we put satellites. The first is low Earth
Yeah.
orbit, which is technically below about 2,000 kilometers altitude. Most satellites are actually
Complicated.
closer to
There you go.
700 kilometers altitude, but the technical definition is below 2,000 kilometers altitude. These are primarily weather satellites, communication satellites, imagery satellites, and military
You have a
satellites.
girl?
Now, the next thing above 2,000 kilometers is medium Earth orbit.
Hmm?
This is where mostly our GPS satellites are at. And they're around
I'm not
20,000
answering
kilometers
that.
altitude. And they have orbital periods that are about 12
I like to
hours, which is
separate my
half a day. And
personal
so
life.
they basically have this ability to come back.
What answer do you want? You want me to say yes or you want me to say no? I'll say whatever you want. I can just lie to you, honestly. So,
Over the same longitude every day, which is an important and interesting feature of the orbits. Then the next one, you go out even further and you're at geosynchronous orbits. And geosynchronous orbits are around 35,000 kilometers
I'm not,
altitude.
I
They're mostly
genuinely,
used
like,
for
I'm not answering
communication
that
satellites and
because
weather
I don't know
satellites.
you,
One of the
you know?
primary important things about an
It's not even a deep question, you know? Everyone be on this channel. My family, cousins, uncles, sisters. I'm not answering that. They're probably not gonna watch this, but you know, no one goes to a 2-hour live stream and just rolls it back.
an orbit is the inclination of the orbit. The inclination of the orbit is the angle between the satellite's orbit as it
Like to keep my
goes
life private.
through the
Okay. And I might know you in real life.
equator. So as it's going
Deborah, get
from
on my chat.
south to north, it makes an angle with respect to the equator, and that angle is the orbit's inclination. Interestingly, the inclination, that angle, if it's below 90 degrees, also marks the angle between the satellite's orbit as it goes through the equator. And they have orbital periods that are about 12 hours, which is half a day. And so they basically have this ability to come back over the same longitude every day, which is an important and interesting feature of the orbits. Then the next one, you go out even further and you're at geosynchronous orbits. And geosynchronous orbits are around 35,000 kilometers altitude. They're mostly used for communications altitude.
Oh no, I wasn't talking to you. I'm on the phone with somebody as well as on the stream. I wasn't telling you to get out. I'm on the phone.
They're mostly used for communication satellites and weather satellites. One of the primary important things about an orbit is the inclination of the orbit. The inclination of the orbit is the angle between the satellite's orbit as it goes through the equator. So as it's going from south to north, it makes an angle with respect to the equator, and that angle is the orbit's inclination. Interestingly, the inclination, that angle, if it's below 90 degrees, also marks the highest latitude it reaches and the lowest latitude. So here are three examples. The first one on the left is an
Mathematician Miles
equatorial orbit.
Morales
So the
beefing in
satellite
my
is
chat
basically
there, bro.
staying in the equatorial plane of the Earth. And so it has a zero.
The mathematician and Miles Morales, Spider-Man, are beefing in my chat. Hmm? You should have been asleep. You can mute me. You on mute? You want to hang up? Hmm? You gotta be up in... What time are you waking up? 7? So you wake up at 5, you'd be fine. That's 7, wait. 7 hours of sleep, you'll be alright. That's a lot of sleep. You need only 6. Okay, you wake up at 5. Are you going to E1A? Yes. Are you going to E1A? It's like 30 minutes away. You be alright. You're going to sweat. You're going to run. Put on some deodorant. Go shower right now. Okay, so why do you need to shower in the morning when you're about to go? It doesn't matter. You don't shower before you... Mm.
0-degree inclination. The one on the covering the entire in the middle is an inclined or characteristic that they go over the entire Earth. If they pass over the poles, that means they're going from pole to pole and they're covering the entire globe. And so if you want to see the entire globe, then you want a really high inclination orbit. And most weather satellites want to see the entire globe, and so they usually have really high inclination orbits. Then there's this special orbit called a sun synchronous orbit, which we basically put at a very precise altitude and inclination that stays in a fixed local time. When we talk about the definitions of some of these things, we have what's called the ascending node, which is as the satellite is going from the south to the north, and then when the
Hmm? Mm-mm. Yes, probably in like 30 minutes. Or mm.
the orbit is going from north to south, it is the descending node. So in inclination that stays in a fixed local, the definitions of some of these things, we have what's called the ascending node, which is as the satellite is going from the south to the north,
Okay,
and
go
then
to
when
sleep.
the orbit is going from north to south, it is the descending node. So in every orbit, you basically go around the Earth in a complete circle, and you go through two phases. The first is that you go through the ascending node, and then as you're going down, you go through the descending node. Ascending node, descending node. Let's talk about what's called a sun fixed coordinate system. So when we talk about orbits, we basically have the orbit going around the Earth, and underneath that orbit, the Earth is rotating. And the satellite orbit plane is actually in sort of a local time of ascending node plane. And let's go through what that really means. So in order to understand that, let's talk about local times. When we look at the Earth with respect to the sun, we have towards the sun, which we define as noon. If we go away from the sun, we have midnight. And then we have dawn and we have dusk. We think of it as the sun is coming up and the sun is going down. But really, the Earth is rotating through this coordinate system, this sun-fixed coordinate system. And it basically stays like this with the Earth rotating underneath it. The local time stays fixed, unfixed in the sun. Away Earth node at orbit, the Earth is rotating. And the satellite orbit plane is actually in sort of a local time of ascending node plane. And let's go through what that really means. So in order to understand that, let's talk about local times. When we look at the Earth with respect to the sun, we have towards the sun, which we define as noon. If we go away from the sun, we have midnight. And then we have dawn and we have dusk. We think of it as the sun is coming up and the sun is going down. But really, the Earth is rotating through this coordinate system, this sun-fixed coordinate system. And it basically stays like this with the Earth rotating underneath it. The local time stays fixed. Satellites orbit in this local time. The orbit stays fixed while the Earth underneath rotates. So this example is showing what's called a 3 a.m. local time of ascending node. As the satellite is coming up from south to north and it's crossing the equator, what is the local time? We can see in this that it's...
What'd you say? I'm busy. I'm not listening. What'd you say? I didn't hear you.
You did.
Mm-hmm. Never. Never.
Where you come?
I'm not coming. Hmm? Too far. Sorry. Hmm? Last time I came there, I got an attitude.
What?
You heard me?
Can you not remind me of that day?
Hmm.
Was that my fault?
I don't know.
So in order to understand...
Mm-hmm. And drive 4 hours to, you know, deal with, deal with, deal with, um, deal with problems. I'm not. Go to sleep. Put the phone down.
That, let's talk about local times. When we look at the Earth with respect to the sun, we have towards the sun, which we define as noon. If we go away from the sun, we have...
Can't even pay attention to my video. I'm gonna end this stupid stream. Not stupid. Goodbye.
Don't do my
Not you.